All right, welcome back, physics students. Hope you guys are doing well. Miss you all a ton. Still down in my classroom, just taping videos, trying to get things uploaded and get ready for the week. So we're moving on to chapter 20 on gases, and then from there we'll take another little jump off. And I'm trying to figure out if we want to go with sound next, and light, and electricity, or we're going to go another route. So stay tuned for that. But let's finish up, since we're talking about solids in the week one, and we went liquids last week. We're now going to move into gases. So let's go through our notes, talk about this, and I'll upload this as well online. All right, chapter 20, gases. So gases are very similar to liquids in since they both flow. So if you think about that, you turn on a faucet, water flows out of that. But then gases themselves can flow. If you think about a propane tank and you hook it up to your barbecue, you turn it on, that gas flows upwards. And if you light a match to it, you can actually cook something on it. So the difference in this is the amount of space between molecules. So within liquids, they are actually attracted to each other. So we have some cohesion usually that's taking place within those molecules, that the polarity of it. But within gases, these guys are spreading far apart. So they're not stuck together to be able to form themselves into a liquid. But if you can compress them far enough to, you can. Just in the same way you can take gas and form it to a solid. So you take carbon dioxide under extreme pressure, you can make it to a solid, but it won't make it back to a liquid stage. When molecules that interact with each other within gases, so they collide with each other, one gains speed while the other loses speed. So kinetic energy exchanges unchanged. So we're basically, think about this as like shooting a billiard ball. One billiard ball hits the other. It transfers that energy completely without a loss of it to the other. So our atmosphere has no definite surface like the ocean, but gases just don't take off into space. They do start to dissipate, as in the amount of density of molecules, the higher we go within our altitude. But part of it's due to gravity that keeps them in there, and part of it's the motion of energy. So sunlight helps this happen. But if you go up within the atmosphere, unlike liquid I talked about within the density, it stays the same. As you move upwards, those molecules get farther and farther and farther and farther apart from them. Remember, like for density, we're talking about mass divided by volume. So if your volume starts to increase, your density is going to be less. So 50% of our atmosphere is below 18,000 feet. So think about Mount St. Helens. So 50% of our atmosphere is below that. 75% is below 56,000 feet, so below where airlines go. And 99% is below 100,000 feet. So it's very small and fragile. Right now, I know during the shutdown, we're actually seeing a healing of the ozone layer due to less emissions and degradation to our atmosphere. So at sea level at 0 degrees Celsius, 1 cubic meter of air has a mass of 1.9 kilograms. But if you heat that air up to 30 degrees Celsius, you're going to see that it's going to decrease in its mass. So as you increase the temperature, you actually decrease the density of it because those molecules start to move apart. So I think I said that right here. As the air temperature increases, let's see, yeah. Because it's expanding. And another way of thinking about that, go back to like the solids. And I had that metal hoop, and I stuck it, or ball, and I stick it through the hoop, and it works great. But if I heat up one of them and not the other, it doesn't stick through because those molecules slightly expanded. Changing air pressure is how we predict weather. And living on the coast, we're always constantly looking at those pressure systems and seeing how they might form to see what's coming. And one of the other tools that we use is a barometer, and it measures the actual atmospheric pressure. So you guys might have seen these before. Your parents might have one hanging on a wall. You might have seen an electronic one, but it's a way of measuring that density, the atmospheric pressure. So the common one we use is a glass tube that's longer than 76 meters, and we fill it with mercury. And remember that the density of mercury is extremely high, so it's a very, very heavy metal. And that allows the atmospheric pressure pushing down on the bottom of the barometer to make sure that pushing upwards within the tube that's filled with mercury, the distances have to go extremely high. Because if you did something like water, so water go back to chemistry, 4.184 joules per degree Celsius per gram of water compared to mercury, you would have to have a very, very, very tall column of water to be able to see the atmospheric pressure. And what happens within this is we actually have a vacuum that's created because the pressure pushing down from the atmospheric pressure pushing on the mercury in the barometer pushes it up into the tube to where we actually see a difference in that. So here's how I break it down for you guys to help you out with thinking about a barometer or also within drinking through a straw. So it's not that you're actually sucking things up, and it's not like the barometer is sucking things up. So you grab a glass, you throw in some ice cubes, some soda, you throw a straw in it, you start sucking on it, and you're like, I just sucked up all this awesome soda juice goodness, whatever. It's not that you're sucking it up. It's that the liquid itself is being pushed into your mouth. And it's all about pressure differences. So it's being pushed up by the pressure of the atmosphere that's pushing down on the liquid in the glass. Since now the atmospheric pressure is less on the inside of the straw, water, or in this case, soda, is going to be actually forced upwards. So it's not that you're sucking it up, it's that it's being pushed upwards because of the loss of pressure. So Boyle's law. So this is all about pressure. So I use this as a full tire for this concept. So a full car tire has a higher density of air molecules on the inside than the outside of it. So we think about that. And a way of thinking about that too, just as an outsider, is think about the tire. It's supporting the weight of the car. So the car itself is very heavy. So those molecules themselves have to be like pushed together pretty tightly. So once the density of the tire is increased by adding air to the tire, the pressure is increased. So you go from 25 pounds per square inch, PSI, to let's say 35 pounds per square inch, which is a common number for most tires to run on. If you decrease the volume of gas in the sealed system, the density and therefore the pressure will increase. So I'm decreasing the volume, I increase the pressure. And on the flip side, if the volume is decreased by half, the pressure doubles. And if I decrease it by a third, its pressure triples. So by confining the space, by sticking more of a fluid in there, like a gas, I increase the pressure. Okay, so an object surrounded by air is buoyed up by the force equal to the weight of the air displaced. So if a mass of a 1 cubic meter object is greater than 1.2 kilograms, it will fall to the ground when released. So this is a magical number right here, okay? That 1.2 kilograms per cubic meter. So if it's anything less or heavier than that, it falls, or more massive. Things that are less rise. So things like, let's say, a balloon. So you get yourself a helium balloon. If you actually figured out the mass of a cubic meter of that, you find it's way less than 1.2 kilograms. That's why it floats. This is the same reason we unfortunately used Zeppelins back in the day, because hydrogen gas, being very, very low, has a very low density, allowed it to rise relatively quickly. So we used hydrogen to fill Zeppelins, and unfortunately, the Hindenburg is the one that you guys know of that unfortunately killed people in a horrible accident. So Bernoulli's principle. So in talking a little bit about Bernoulli's principle, my chair. So most people assume that atmospheric pressure increases during storms, that where we have heavy winds and things like that, that we're on the coast and we deal with. But that's not the case. A 60-mile-an-hour windstorm has less molecules per given area than a day with no wind. And the reason why is it's increasing its speed. As those molecules, as we have an increase in kinetic energy, we start to have a decrease in pressure. So when the speed of a fluid increases, its pressure decreases. And this is all fluids. So as low pressure systems build offshore, we experience clouds, wind, and rain. When we have high pressure systems, we have warm weather. So right now, outside my window, I can see a storm coming. It's sunny right now, but I can see it's nice and dark off in the distance. And that means that I'm having a low pressure system of which it's going to have wind and rain. Eventually it'll pass and it'll get sunny. And though these systems in some places are very steady, so let's think about like a desert. So it's hot during the day and it's hot all day long. For here, being at the shores or at ocean shores, as things heat up inwards, remember we have a very large amount of cold air offshore. And if you think about thermodynamics and trying to find the equilibrium between temperatures, that hot air brings that cold air in offshore, and that causes more winds. So on days, if you guys have been here long enough, those days where it's like 70 degrees and people are like, it's gonna be 70 today. And I'm like, yeah, it's gonna be 70 for a brief minute, and then gonna get windy, and then it's gonna get cold. So sometimes it holds off, but a lot of times you guys have seen it gets windy. And it's all about those pressure differences of the molecules that are heating up. Cold air over the water, molecules kind of packed together. Hot air over the sand, molecules will spread apart. They want to find that balance. Bernoulli's principle, continuing on here, when the speed of a fluid increases, the pressure drops. And this is one of these things, it's hard to think about sometimes because when we think about high pressure systems, we're like, oh yeah, It's moving very fast, got a lot of force in it. It's not really that. It's the amount of fluid, either liquid or gaseous, in a confined system that's putting pressure outwards on that system. So as you get smaller and smaller and smaller in diameter of a tube, you increase the speed, but you decrease the pressure. And think about that, and I know I don't have a whole lot of things. So this is, let's say, a pipe. All the water pressure on here is equal, and I have a large amount of fluid going through here. So a large amount of pressure that's pushing outwards. If that gets smaller, confined to a smaller space, there's less force pushing outwards. So that speed will increase, but its pressure will decrease. So for a steady flow of an ideal fluid free of internal friction, there are three kinds of energy: kinetic energy due to motion, work associated with pressure forces. So remember, work is all about force times distance, so pushing outwards, and gravitational potential energy due to elevation. So if we're talking about something like a dam, and taking a dam and taking the water from there to be able to power a hydroelectric plant. Like, how do we change that water coming through? How much do we have to confine it or expand it to be able to turn those gigantic turbines to be able to produce energy? All right. So if the elevation of a flowing fluid does not change, then an increase in speed means a decrease in pressure and vice versa. I might mean the elevation of flowing, let's say we're just talking about a hose. So we're not talking about something on top of a mountain. So the decrease of fluid pressure with increasing speed does seem weird, but this is the systems of physics. As you decrease that area, you increase the speed. Yes, increase the speed. So we can draw things that actually could show this. So though the hose of a firefighter, so they're putting out a fire, the pressure in that hose is super great. As it comes out, its speed increases so it can come a long distance. But still, since it's going at a very fast speed, it can have a lot of force. And that's why you can see some of these firefighting hoses, that's putting out a fire and it's like knocking out windows and it's breaking part of the house. And that's because that confined pressure system has increased its speed, and now it can go a longer distance. So this is the same concept also within flight. So if you've ever been on an airplane before, the pressure above the wing is less than the pressure below. And because of that difference in pressure causes it to have lift. So we have upward lift basically. And if we have lift that equals a weight, you can actually fly horizontally. So things like gliders have very long wings that increase the surface area and increase the amount of low and high pressure systems over and under the wing. And it allows these guys to travel very slowly. But things like fighter jets have a much smaller surface area than a glider and a very gigantic engine that allows these guys to be able to go much quicker. So continuing with some of the processes within Bernoulli's principle and how this works is, let's say we're talking about like a tornado coming or a great storm. So let's say we're on the South Carolina shoreboard and there's very large winds coming in. They're saying it's going to blow 90 miles an hour. People think about the winds blowing the roof off of a house, but it's not so much that it's getting blown off. It's literally getting popped off, because as the wind is moving on the outside, excuse me guys, as the wind is moving on the outside, its pressure is decreased. If you're inside the house and there's no wind, that pressure is increased. That change in pressure sometimes can have that roof become ripped off of the house or popped off of the house, so to speak. So you might see that in some places, especially on the coast, some of the larger houses that have bigger roofs, you might see those vent little things on the top, and it allows air, that pressure system during great storms, to be able to equalize a little bit more, so that way you don't lose your roof. This also applies to spinning balls, so things like a soccer kick could use Bernoulli's principle to make a curveball, as well as softball, baseball, and even golf. As those pressure gradients are different on one side of the ball than the other, you have curvature. So this is how you can throw a slider or a curveball, or even on the case of, let's say, a golf ball, be able to hook it around a tree based off of that spin. And one of the last things here that's kind of a weird topic, but it happens all the time, depending on where you're at, depending on how big and small your shower is, and if it comes in the bathroom. But if you've ever taken the shower before, and all of a sudden the shower curtain blows in, and it touches you, and I know we're like, oh, it's like the worst feeling. You're like, gosh, I'm all clean, and it touched me. I'm still clean, but it still feels weird. The reason why is the pressure inside the shower is less than the pressure outside, and it's due to the water moving. As that water is moving inside the shower, it's actually lowering that pressure than the outside. So the outside is still, and as that still high pressure system and that low pressure doesn't move in here, it causes that to bow in and provides an escape for that air, and then it touches you and you feel gross. At least I do. So hopefully this helps for chapter 20, guys. Again, reach out for help if you need anything. You guys know I'm always around. I miss you tons. I know we're getting closer to the end of the year. We're still going to keep plugging away. I know for you seniors, you're getting kind of antsy, but we can do it. We'll stick together, and we'll be okay. So I miss you guys a lot, more than you know. But I love you guys, and I'll talk to you soon. Peace.